I'm about to turn it over to Adam, and I just wanted to share a little bit about Adam. Adam has a really deep, a strong connection to water. We were just chatting about this as we were waiting for folks to join, but I learned that Adam started his career and his connection, his love affair with water, drilling wells in Ghana as a student. He was literally bringing water to people in communities that didn't have access to fresh water in close proximity. They would sometimes have to walk a day or more to get water that was not necessarily safe to drink or to use. And so he spent about 9 months in Ghana doing that. And then over the course of time, that's where he really felt like he could make a big difference. Now he's managing recharge efforts in California. He's actually the recharge planning manager at Orange County Water District. And he just got back from Cape Town, speaking at the ISMAR conference, the 12th annual. So we're very excited to have Adam here today. Thanks for being with us, Adam. And I'm going to stop share and turn it over to you.
Hey, I will share my screen then. All right. You see that okay?
Still loading. Yep, looking good.
Great. Well, thank you, Megan, for that introduction. Great to see everybody online. I know you could be a lot of other places at your lunch hour, so really grateful that you're here and you attended this webinar. Appreciate your time, and hopefully we'll present some interesting things. With this project, what we're going to be doing is talking about kind of using an old technology, riverbank filtration, which has been done for over 100 years in different parts of the world, and kind of putting a different twist on it for a different purpose. And I'm really hopeful that this technology can really be of benefit to people not only in California, but other parts of the world that are involved in managed aquifer recharge. So I think before we get started, though, Megan and I would like to give a quick poll just to kind of get the sense of where people are in the managed aquifer recharge space. So I think Megan's going to put up a poll here and we'll have everybody fill that out.
Sorry, 1 second. I pressed the wrong launch button. There we go. This is another two-parter. You'll have to scroll down to see both question 1 and 2. The first question asks, how knowledgeable are you with respect to managed aquifer recharge? 10 being, ask me anything, I'm a professional. 0 being, what's MAR? And the second question is, are you or your agency or company involved in MAR? And there's a couple of choices there for you. If you're just here to learn because you love a good water recharge story, amazing. You're not involved yet, but you're dipping your toes in soon. You've started, MAR's on your radar, or you're absolutely knee-deep in MAR and loving it, schlossing through with your galoshes on. Looks like we're still getting a couple responses. Give folks a few more seconds to play along. All right, let's close out in 3, 2, 1. All right, sharing out the results. Can you see that, Adam?
Yeah, so it looks like we got experience, a wide range of experience here. That's wonderful. And then got a big group that are here just learning, and then a big group that are knee deep and loving it. So we've got a great spread here. So fantastic. Okay. Well, thank you everybody for that. Let's get started. So some of you, just to make sure we're all on the same page in terms of, who are we? Who is Orange County Water District? Well, we're located in Orange County, California, not Florida. And we're cover about 350 square miles. We have about 2.5 million people in our area, so pretty dense. And we're a semi-arid region, only 14 inches of rain per year, typical Mediterranean climate of Southern California. And Orange County Water District is a wholesaler. We don't retail the water. These parties that you see on the screen here are our retailers. They're our customers. So they pump the groundwater and they pay us a fee for that water, and then we use our fees and revenues to do all the different projects that we do. So we were formed in 1933. We're kind of a Sigma poster child from way back when. There was a lot of overdraft and seawater intrusion taking place in Orange County back in the turn of the century in the 20s. So we were formed to address some of those problems. And So we provide 85% of the drinking water supplies in the area. The other 15% is imported water from Northern California, the Colorado River. We have 10 board members, and we also protect the right to the Santa Ana River water. That's another reason we were formed in 1933. That's just OCWD at a glance. We're blessed to have a huge underground aquifer in Orange County. It holds about 66 million acre-feet, but obviously we can't use all of that water. So we only use about 500,000 of that 66 million. And that's our operating range. We try and keep the groundwater basin relatively full in that range to avoid subsidence of seawater intrusion. So that's important, but it's just a big layer cake alluvial aquifer that you see in many places in California. So a little bit about our infrastructure that we have here in Orange County. So at the far upper right, you see Prado Dam. That's a U.S. Army Corps of Engineers dam that was built in 1941. That's important for stormwater capture. And that stormwater is released downstream to our recharge basins, which are located in Anaheim, adjacent to the Santa Ana River, and in the river itself as well. And then down toward the coast, we have our seawater intrusion barriers, 2 of them. And the Talbert barrier is supplied with recycled water, 100% recycled water. And then that recycled water is also pumped up that red line at the pipeline that takes it up to our Anaheim recharge basin. So very important source of water for us now. So kind of drilling into our facilities up in Anaheim. So we have, 1,500 acres of land. We could not afford to buy this land today if we tried. That land was $27 an acre back in 1936, and now it's about $2 million an acre today. So we're really fortunate we started early. And so we have more than 24 different facilities. And what I want to draw your attention to in this graphic here is that you kind of put our facilities into 3 different buckets. One bucket are surface water flow facilities where the water is constantly flowing, and that's shaded in the blue. That includes the main Santa Ana River and off-river channel basins. Then we have the green Santiago Basin and Burris. Those are former gravel pits, and those are primarily just recharge water when they're full and not when they're empty. So they're a different animal compared to the purple, which is really the focus of our talk today. And those are what we call the terminal recharge basins. And these basins are your typical recharge basin where the water comes in and then it just sits. And because the water sits, all the suspended sediment and solids in the water you're feeding it settle out on the bottom and clog. And so these are really the facilities that are most prone to clogging and of most interest in the study I'm going to be presenting to you today. So we have a pretty diverse water supply. As I mentioned, GWRS, the recycled water now is our largest component of recharge to the groundwater basin. And that's beautiful because that's 365, every day of the year, we're getting that water in the ground. The base flow coming down the river is pretty consistent. Natural recharge is consistent, but the storm flow is really the wild card. And so that's really with the changing weather patterns and everything, it's so important to make sure we can capture all that storm flow that's coming our way and not lose any of that to the ocean. So why are we doing this study? Well, all recharge facilities clog. That's a universal kind of a golden rule when it comes to MAR. It's all going to clog at some point. So you need to be ready for that or have steps to deal with it. And for us, because we're adjacent to the Santa Ana River, we get a lot of suspended sediment that we bring into our system in tons per year, every year. And so it's really a key constraint in our ability to recharge water. And as I mentioned, land is $2 million an acre. So we want to make sure we can get the most out of every acre of land we have. And that's really what's driving the research we're doing on clogging. So the whole idea is, can we increase our recharge capacity by reducing clogging? And I always love throwing this slide up here. If any of you know Herman Bauer, he was kind of at the vanguard of MAR for a long time, really knowledgeable, respected man in the field. He's passed away, but I always like sharing this quote because it really does show that, clogging is the bane of all managed aquifer recharge systems, and it's something you need to be aware of and ready to deal with no matter what system you're running. So this graphic here shows the percolation rate in one of our basins called Miller Basin. And the red line is what the average river water percolation rate would do over time. It's pretty rapid decay. But the blue and green lines are recharge rates we see with imported water or recycled water. And when we did, so it's the same basin, just fed a different water source, 100% of each of these supplies over time at different times. And you get a direct comparison of how the basin performed. And what we found is with this purified water, the imported water and recycled water, we're getting double the recharge capacity in that same basin. So that really drove the point home of how clogging is impacting this basin. If we can somehow clean up the river water and make it better and reduce the clogging potential of that source of water, we could potentially double the amount of water we can get into the ground. So that's really a big driver for us to do this work and find out how we can do that. So to kind of figure this out, we undertook a really large sediment removal feasibility study. And so basically what we did is we took different technologies such as cloth filtration or active flow, or flocculation sedimentation, that's the very typical treatment technology, and treat the river water with these different treatment technologies, and then also put them into the concrete test cells that you see at the top. And this is really important because it's almost like a medium scale project where we're actually putting the product water from these treatment systems onto the concrete test cells that are filled with native sediment. And what we found was really interesting, and I think really surprised the engineering community, was any method that used a polymer, a flocculant, or any kind of chemical pre-treatment to reduce the sediment load and get the sediment to drop out, even though it created water that had low turbidity, once you introduced it into the concrete test cells, they ended up clogging. And we suspected that's because there was carryover of the chemicals, and the chemicals started interacting with the native fine-grained materials in the sediment and start to create clogging. But the two methods that did not cause clogging like that was riverbed filtration, or RFS, and cloth filtration, because we were able to use those two methods without any chemical pretreatment. And so it's just purely mechanical filtration with no chemical addition. And that did result in increased percolation rates over the baseline. So that was an important finding of this study. And I think it's really important to keep in mind as you look at strategies to reduce suspended sediments in your source water. So the cloth filtration, we did it on a small recharge basin for several years, and it was able to remove suspended solids, but the capacity or the ability of the cloth filter to remove sediment loads is pretty limited in a finite range. And so it didn't turn out to be very suitable for high levels of TSS. So not really very useful in the broader scale in our system. So not something we could really scale up in a cost-effective manner. So we shut that system down and got rid of it, basically. So getting to what we're talking about today, riverbank filtration is kind of what we're doing on in a slightly different way. But this technology has been used for years in Europe and all parts of the country. This graphic here is from Sonoma Water up on the Russian River. They have 9 of these riverbank filtration wells that they use for treating their water prior to use. So we kind of took that same approach, and this picture here showed the actual construction of our pilot system that we did put together, and it's just basically like a reverse French drain. You're just digging down and putting these PVC pipes underneath the surface about 3 feet, putting gravel over it, and then covering it back over with the native material. So just using native sediments for filtration purposes. So just like you do for riverbank filtration, but we're not using that water for potable use. We're using it for recharge purposes. So the pilot system we built was expanded to a full-scale demonstration project. And so what you see in the red boxes are two sets of laterals that we built. And I'll give you a more detailed graphic of that. But all these laterals that cover about 10 acres, and they go into a dedicated supply pipeline, that orange pipeline. And then that water is conveyed to a downstream recharge basin called Olive Basin. So that Olive Basin only gets filtered water from this project. So this is the project we've been working on for about 8 years and testing it in all kinds of different configurations and different modes to assess its long-term performance. So as I mentioned, we use PVC pipe for the pilot, but we also used a different style of construction for the demonstration project called rain tanks. These are made by Atlantis. They're used a lot in the flood stormwater capture industry, underneath parking lots and other ways to capture stormwater. And so we installed these to see if that would also provide a benefit in comparison to the PVC pipe. Here's the picture of the rain tank being installed. You put them together, they're like Legos. You snap them together and then you wrap the geotextile fabric around them. And they just serve as a conduit for water, just like the PVC pipe does. And so we put together these series of manifolds with alternating types of material, the PVC pipe or the rain tank. And we also looked at the orientation of these tanks to flow. Does it make a difference if they're perpendicular to flow or parallel to flow? Just trying to look at all the different perturbations that we could make to assess future design parameters that we might want to use for this type of project. So I mentioned this filtered water was then fed into Olive Basin, and we also constructed a monitoring well near Olive to look at the water quality impacts of the water after it's already been filtered once. Do you see additional changes in water quality after it's recharged again? So let's talk about the results. We've been testing for over 8 years. A lot of performance and water quality testing that we can present here today. I'm not going to go into the gory details, but just some of the highlights. So Olive Basin performed well from 2015 to 2033. I think the one thing I want to draw your attention to at the bottom line, that's the percolation rate over time. Because of where the offer of the system is situated in our recharge system, it primarily receives floodwater. So it's mostly active in the wintertime. And then in the summertime, when we're down to base flows in the river, we're not able to supply water to the system. So it's somewhat erratic, which made interpretation of the results a little more challenging, but not impossible. But that's why you see so much spikiness in the data, because of the supply constraints to the basin. So the bottom line is the system was extremely effective. Over time, it removed 96% of the suspended solids. So very pure, sometimes non-detect coming out of the system. This is a log scale, by the way, so don't get, make sure you keep in mind that the log scale. So the blue is the product water versus the source water. So extremely good result, and we did not see any type of degradation over time. The system continued to perform very well over the this entire time period. So what does that mean for, well, before I get into performance, other water quality improvements we saw were TOC and DOC removal, 50%, which is pretty consistent with the literature, soil aquifer treatment. What's really fascinating is, you're talking about very quick, travel time through the soil, on the order of 3 to 4 feet per day of travel time. So you can see that organics removal in MAR is very effective, despite the short travel time here. And some of the CECs that we saw removed a pretty typical removal pattern that you see, some removed, some not removed. But if you want more on that, you can read the final report, which I'll give you a link to at the end of this presentation. So what did we get out of this? So The red line that you see here on this graphic, that's the performance of Olive Basin with unfiltered river water. That's kind of what it would do typically on average. You could see it would fill up and clog pretty quickly, just like Miller Basin that I showed you earlier. And all those other lines are the riverbed filtration percolation rates over time. And you can see that we all got much higher rates, up in the 20 CFS range. And for a long period of time, we can go like a year between cleaning, where with unfiltered water, you'd have to clean it after just 3 or 4 months of operation. So how do we interpret these data? So what I did was I took a graphic and said, okay, over a 500-day period, how many times would I have to clean the basin using unfiltered water? And that's the red line that you see there. You see the river water cleaning period. So there's 4 cycles of operation shown here with unfiltered river water. And then I took the long period of time we had for several of the runs we had and kind of tried to project, if I had had a constant supply of water to the basin for the time period, what would the clogging have been? And that's what that dashed line shows you. And so if you look at the volume under the curve, the red and the dashed line, that's what's in that box there in the upper left corner there. So with unfiltered river water, you're getting on that time period 5,500 acre-feet. And with the riverbed filtration, based on the projection, you're getting more than double that volume. And this matches up really well with what we saw in Miller Basin on that slide I showed you earlier. So it's nice to see a repeat of that doubling of the recharge capacity using a different source of water in a different basin. And so it gives us a lot of confidence that this is a real benefit that's achievable on a bigger scale. And by the way, this is the permanent feature of Olive Basin now. It would always be receiving this filtered water forever. We're going to leave that system in place permanently because it's giving us a great benefit here. So just some other performance metrics I wanted to mention here. We did not see any difference in the slotted PVC pipe versus the rain tank in terms of volume or performance over time. So it's really a wash on that one. The orientation of the lateral did not make any difference, whether they were parallel or perpendicular to flow. We did not see any long-term performance decline. I think some people were concerned that the suspended sediments might get bound up in the riverbed sediment and not get cleaned or washed away. But because there's always surface flow going over the top, I was able to keep that surface pretty clean. We did notice a decline in per lateral performance when all of them were open. So what that meant was that there were some laterals that are too close together. And so if you have everything open, you start to cannibalize the performance of the other laterals that are nearby. So spacing turned out to be pretty important. You can put them too close together and you're still going to get the overall same flow rate, but the per lateral performance is going to suffer. So there might be some obviously optimization that could be done to make sure those are spaced at the right distance apart so that you're not overbuilding the system. So here's a picture of what we do right now when we divert water. So this is our Imperial Rubber Dam. This is at the very top of our system. And most of our system operates by gravity. And so we start at this location, we stop the water, and then we divert it. That's the big arrow going to the right. That water is diverted, and that goes down to our terminal recharge basin that I showed you earlier. And then we also bypass water around the dam, put it back into the river. But this allows our operators to completely control the volume that are going to both locations. We have flow meters on both of these, and so we can carefully feed water to the system at this location, and we have other flow control points downstream as well. So I show you this because the big idea is to divert water in a different way. So this graphic here kind of shows you what we're currently doing. We've got Santa Ana River water coming down, we've got a rubber dam, we stop the flow, we divert it to recharge basins or back into the river downstream. So that's our current operation. So the vision of using riverbed filtration will do the following. we'll put the riverbed filtration system under the river and divert the filtered water off the river and leave the unfiltered water in the river that goes downstream. And so rather than diverting on top above, you're diverting below. But by doing that, you take advantage of the filtration properties of the riverbed and then take advantage of that filtered water and then increase your recharge capacity. So that's kind of the big idea. Hopefully that graphic kind of simplifies it, the concept. So where's the biggest bang for the buck? What do we do with this technology? Well, I mentioned before, the terminal recharge basins shown in the red box are the ones that are most prone to clogging. They're the ones where the water comes in and sits and the solids settle out. So these are really the ones you want to try and target in any kind of expanded recharge system and, you know, potentially double our recharge capacity like we've seen in Olive and Miller. And one thing we have to take into consideration in our case here is we have a pipeline that connects these offstream basins to the river called the Warner Transmission Pipeline. And right now that pipeline capacity is fine, but if we purify the water and make it cleaner, there's going to be a greater capacity downstream than that currently exists that we need to look at potentially maybe upsizing that pipeline to account for the cleaner water that we might have in the future. So here's the picture of the recharge basin, Terminal 1, the Anaheim Lake, Miller, Kramer. So these are the basins that we're targeting for this riverbed filtration system. Now, to analyze the potential yield we might get, we used a recharge facilities model that was developed in 2009 using GoldSim software. It's a really great model, great tool that we've used for a lot of planning exercises over the years. And the secret sauce behind this model is it includes percolation decay equation that we've developed for our facilities based on a lot of research that we've done. So every basin in the model has its own percolation decay equation. Some of them are similar, but some are unique and calibrated to that particular basin. And that's really what makes the model work. And we're able to calibrate the model because we have those equations built in. So very useful, very handy, but really important to account for clogging if it's going to be an accurate model. So using this model, we said, okay, what if we had no clogging in those downstream basins? What could we get out of it? And this is what we came up with. If you see the graphic there is the total annual recharge with no riverbed, that's the baseline. And then if you put in the riverbed filtration and then riverbed filtration with increasing the water transmission pipeline diameter or capacity. And the one on the right is really the more interesting one. That's the average annual increase that you would get from the project. So you can see with riverbed filtration, we're looking at about 7,000 acre-feet per year. And if you increase the pipeline, it's another 9,000 plus acre-feet per year. And to put this in context for people, you know, the value of water in Orange County is really based on the alternative source of water that we can buy, and that is imported water. So imported water, in round numbers, we use $1,000 an acre foot as the value of imported water. So if we lose water to the ocean, that water, if we can get it into the ground, the value of that water is really $1,000 an acre foot because our producers would have to purchase that water to offset the decreased amount of groundwater they can pump. So the more groundwater you provide, that offset imported water at a one-for-one basis. So this project here, Riverbed Filtration, that's $7 million worth of water a year. So that's a pretty high value there. So that's kind of a useful metric that we have here in Orange County to do our cost benefit analysis, as we know that the value of imported water is $1,000 an acre foot. So anything we can do to get water in the ground that's lower than that is probably going to be a good project. Now, we're not the only ones that have done this. Talking to people at Turlock Irrigation District, and they installed this type of a system in the Tuolumne River to recapture environmental flows that were released upstream. And so they built this system in the Tuolumne River, get 100 CFS out of it. They just put it in operation recently. And so it gives us comfort knowing that other people have done this before. This year, this water is taken off for irrigation purposes and potentially potable purposes as well. The Pajaro Valley Water Management Agency has a project like this in their planning documents where they want to capture water from the Pajaro River and send it to a recharge basin. So this is just conceptual on their end, but it just showed that other people are thinking of using this technology. And the last example I want to show to you is interesting. This is the South Valley Water Resources Authority, JPA. This JPA is really focused on trying to get water out of the Delta. And so they actually want to use this technology as a glorified fish screen, basically, just to allow them to take a lot of water out of the system without hurting fish. So another application of the subsurface recharge technology. I thought that was pretty interesting. And theirs is huge. They want to build it up to 15,000 CFS, so pretty big. So to kind of summarize, the riverbed filtration provides multiple benefits. It obviously will increase our recharge. And the filtered water that we get can mix with other clean water sources that we have available, such as our recycled water and imported water. So we kind of mix those together without causing clogging. If we mix river water with the clean sources of water, it pretty much contaminate that clean source, and it clogs the basin just as if there was no clean water mixed in with it. So having the cleaner water source would give us a lot more freedom to recharge the cleaner sources. And we can divert the water when the rubber dams are deflated. So one of the beauties of the system is underneath the channel, our rubber dams have to be deflated when the flows are about 1,000 cubic feet per second. And so this system here doesn't care, if that flow is 1,000 feet or 1,000 cubic feet per second or 5,000, it's still going to be diverting water off the river. So that's a real benefit as well. And it will reduce the number of basin cleaning that are required. You're going to have less wear and tear on your equipment, less labor requirement, because now you're getting longer run times in your basins. And so that's really a great benefit. So I think when you think about big picture in other areas, like what they do in the Tuolumne River, this represents a technology that could be used to less invasively be able to divert water off of rivers for recharge purposes. A rubber dam is pretty disruptive to the environment. So if you have, fortunately, we don't have fish or other things in our area, but if you do have fish and other environmental concerns, this is a real good technology that could be used to divert water under the surface without disrupting the habitat above. So the final project report for this is on our website. There's a link, and you can also use the QR code right there if you'd like to, and read that report. If you do read it and have any comments, I'd love to hear what you have to say about it. A lot of good information in there. 8 years worth of data in there, so it's just a lot to sink your teeth into, but would love to have you look at that and give me any feedback if you have any. So I kind of wrap it up with our next steps. So where are we going with this? So right now we actually have an RFP for a feasibility study that just got posted to our website yesterday. And you can see the link right there. You can go to our website and download that RFP if you want to respond to that proposal request. And what we really want to do here in this is kind of look big picture and go, what are some design options that we have in terms of gravity system versus the pump system like Turlock irrigation put in, or some combination of both? And what would it look like to build something at a bigger scale and look at the Corps of Engineers and public work constraint that might be on the system and how we build it, and develop a really crude range of cost, because we have the benefit side that I showed you earlier in terms of how much water we can potentially recharge, but we don't really know the cost side. What would it cost to build something like this and maintain it long-term and operate it? And so we really want to do kind of a first cut at a preliminary design for this. And then if it turns out to be feasible and looks promising, then we'll go to a more detailed level of design and really flesh out any potential fatal flaws and other things that we hadn't thought of. So we're excited about this project, really wanting to push it forward and see what we can do and get more water out of our system, reduce our clogging, reduce our costs, and benefit the basin, and do it in an environmentally friendly way. So hopefully you got something out of this and enjoyed it. So I think now we can just take any question that people might have.
Thanks, Adam. We've got two questions, first from Chelsea, and then another question from Gretchen. Let's start with Chelsea's questions. And Chelsea, you are welcome to come off camera, off mute, and engage with Adam if you like. But I'll just start by reading your questions in chat. Are the perforated pipes covered in geotextile as well as the rain tanks?
The answer is no. The perforated pipes were covered in just pea gravel. And I think I like that design better because there was always concern about the geotextile fabric capturing fines and becoming clogged over time. And also just the material would probably degrade over time as well. So I think the PVC pipes with the gravel is something we're going to really be focused on in the future, and not the rain tanks. We thought the rain tanks might be cost effective because of the material cost might be less, but there was a lot of extra labor associated with putting those together and assembling those and putting those in that kind of negated any cost benefit there. So there was really no cost benefit to using those rain tank compared to PVC pipe. So I think for the full design in the future, I think we either go with PVC pipe or wire wrap pipe that you saw Turlock Irrigation District use. Those are all things you need to kind of think about and consider as we move forward.
And she's also curious what the range is for TSS, total dissolved solids, in the raw Santa Ana water.
Yeah, that's a good question. The raw Santa Ana River water has, I think we're up in the 400 range for storm events. Let me scroll up and show you another slide. I think that might help. So this one here shows, the range that we got into, in the 400 so range here in where the system was located. But what we did, and I'm going to show you this picture here, this far left photo that you see there is we actually had a question from our staff about, where the Riverbed Filtration System is located. It's already receiving some water that's been through some pond, some weir pond, so it's had some sediment removal. So what if it was in the main river where there is no removal? You're just getting raw water, unfiltered, untreated in any manner. And so we did that. And what you see here, our operator guy building a mini version of the Riverbed Filtration System in the live river channel. And what we did there is we actually had a pump in that system, and we were wait for big storm event to come through and go in and sample the surface water and the water coming out of this system at the same time to see if there was like a threshold at which if the TSS was too high, the system would fail. And what we found is it did not fail, that even with high loading, and I don't have the numbers off the top of my head, I apologize for that, in the live river, but the data is in the report. It does show that even at higher loading rate that we saw in the pilot demonstration project, that riverbed filtration technology worked admirably even at really, really high loading rates here.
Can I just inject my own question? I'm curious what happens with the sediment that's removed after it's filtered.
Good question. So the beauty of the system is that it's in a river channel or in an off-river channel. So any sediment that's removed basically gets trapped on the surface of the soil and it just gets moved downstream. And so you're leaving the sediment in the river channel and eventually goes out to the ocean. Right now, if we divert that high TSS load into a recharge basin, as I mentioned, it collects on the bottom and it creates the clay layer, and then we have to go in and scrape that out. And we end up with these huge piles of sediment that we have to get rid of at some point. You've got tons of this material coming into our system. So the benefit of this is you're leaving the sediment in the river so it can get transported out to the ocean where it really should go, because we know that beaches and down coastal communities are starved for sediment and material. So it can leave that in the river, and it reduces the need for us to have to try and handle it and dispose of it later.
Maybe kind of related to this, Gretchen asks, how do you clean the recharge basins?
Yeah, so the recharge basins are cleaned using heavy equipment. So we have pump stations in them. We have to pump the water out, let those basins dry so that the clogging material kind of forms potato chips or curled up on the bottom. And then we come in with motor graders and we try and carefully just skim off that clogging layer, the upper 1 inch or ½ inch of material. We try and be very strategic. We don't want to remove the clean sand that's underneath, just the clogging material on the top. So we basically windrow all that material, and then we have a paddle wheel scraper that comes by and picks up those windrows. So it's kind of like what you do in your house, sweep everything into a corner and then use the dustpan to sweep it up into the dustpan. So we're kind of doing that, but on a big scale.
Neat. Camyar just comments that this is a great example of utilizing natural filtration ecosystem services to improve recharge and is also protective of aquatic species. Cool.
Yeah, I can call it a nature-based solution, right? That's a nice buzzword people use a lot, but that's what this is, nature-based solution.
Mhm.
Yeah, thank you, Camille. That's great.
A couple thumbs up on that. Any other questions for Adam? Folks, you're welcome to use the chat, or if you want to use your raised hand or just come off mute and off camera and chat with Adam. We're scheduled for another couple minutes here, 10 minutes or so if we need it. It's also neat to see that some other areas are implementing this filtration system as well.
Yeah. Yeah, and I agree. If you guys think of any questions later, feel free to shoot me an email or contact me. I'd love to chat with you about it. And don't forget to download the report if you want. In fact, I'll go ahead and put up the slide. Oh, sorry, I got these extra slides in here. Sorry about that. There's the report QR code. You can download that and look at it. Got everything in there.
Jamiar was asking lots of comments and hand claps on an excellent presentation. I also really appreciated, Adam, the visuals and the imagery that really helped me conceptualize what you were talking about. And I'm probably the least informed of anyone participating in the LunchMAR sessions. So thank you for such a great presentation. Camille was asking, does this tick off one of the research and data development plan recommendations? Folks know what Camille is talking about, the R&DD plan.
I'm not sure. It's a good question. Is that the DWR R&D plan or?
We have Camille. Did you want to come off mute and say more about that, Camille?
Hello, everyone. Thanks, Adam. Great presentation. Number of years ago, as the network was coming together, actually, it was the inception of the network. 200 some experts put together a research and data development plan to really be able to leverage and improve LunchMAR in California. And about 39 recommendations covering 13 different disciplines or areas, one of which was water quality, is in that plan. And at the forum this fall is going to be an update on what's been accomplished and what more needs to be done on those recommendations. And if not, I think this work can be added to the water quality and recharge improvement part of that plan. Thanks.
It's a great point, Camille. Yeah, if the can be added to the plan, or if it's a checkbox and say, hey, we did this and this is what we found, that'd be great to update the group on that.
Yeah, I think Marissa's on this call, and she's the one who did the heavy lifting on the review of the plan. And so we could certainly add this for the presentation this fall.
Sounds good.
Aisha has a question for you. Did you have to work with Army Corps of Engineers on the Riverbed Filtration System construction? And if so, how did that process go?
Yeah, so we were very fortunate that where we built our demonstration project was actually on our property, not in the main river that the Corps had oversight on. So that's one of the challenges we have going forward, seeing what kind of requirement the Corps would have if we were to build a system, a larger scale system in the live river. And so that's one of the things we're going to need to look at closely going forward. But for the demonstration project that we did not need to coordinate with the Corps or Public Works. You know, we informed them, but it was on our property. And so that's one of the benefits of having some areas of land that we own, that we're in control of, that we can do these kind of projects without getting burdened with all the regulatory approvals, which, as we all know, can be really challenging. So, but the future project, as we consider it, we will probably, require, Corps approvals and Orange County Public Works approvals. So we'll be working with them closely on that.
Is the same true for State Lands Commission?
No.
No. Okay, no requirements to work with State Lands Commission for Valley Project. Cool. Wow, that really saved lots of time.
Yeah.
Resources. Cool. Okay, last call for questions for Adam. All right, Adam, I'm not seeing anything come through. Thanks so much for being with us today, Adam, and everyone. Really appreciate you joining, and we will get the recording of Adam's talk posted to our floodmar.org website in the coming days, and you can see all the other LunchMAR sessions there too, like an infomercial. But keep up the great work. That's really, I feel like Orange County Water District is a pioneer in this area, and it's good to know you're working with Turlock and Pajaro and other areas, and we look forward to hearing more about this in the future.
All right. Thanks, everybody, for your time. Have a great day.
Thank you. Bye, folks.
Thank
Bye.
you.
Thank you.
Thank you.